right, and today we're going to talk about stars, how they're classified, how do astronomers find out how far away they are, what tools do they use, and what methods do they use. Let's get started. And just keep in mind this corresponds with Chapter 26, Section 2 in your textbook, which is pages 838 to 843. Two key points to think about throughout this. First of all, even the closest stars to us are incredibly far away. In fact, that's something we try to focus on throughout this unit is understanding the sheer distance in space between objects. We're actually going to make a scale model of our solar system so we can sort of conceptualize that. But because of the vast distances between stars and galaxies, we actually had to come up with a new unit of measure, and that's going to be the light year, and also new methods of measuring the distances themselves. And also, stars actually share quite a few basic qualities and are organized largely by their color, their size, and their brightness. And we'll use the Hertzsprung-Russell diagram to visualize this. We obviously have a variety of units of measure to fit a variety of circumstances. So, for example, if you're measuring a pencil, you might use centimeters or even inches. A football field's marked in yards, correct? New York to Boston, we probably measure in miles. And the same is true with the Earth to the Sun, or kilometers. But from one star to the next, we need a new unit, and that's going to be a light year. And you can see in this picture here, Proxima Centauri is the closest star to us outside of our sun, of course, and it is 4.3 light years away. So what exactly is a light year? Well, that's the distance that light travels in a vacuum in a period of 1 year, or 9.5 trillion kilometers. Now that's really far. The nice thing about having this very large unit, though, is that it allows us to sort of wrap our heads around these immense distances. So if you look at the graphic on the left, the second from the bottom, you see Earth to Alpha Centauri, which says 4.4 light years on this graphic. Compare that to the Earth and the Sun, which is only 8 light minutes. So what that means is that the light from the Sun takes about 8 minutes to reach us here on Earth. Now compare that to the bottom of that graphic. Earth to the far side of a Milky Way galaxy is 52,000 light years. So you could take your calculator and multiply that by 9.5 trillion kilometers and get a distance in a more traditional unit. But again, that's such a large number, it's very difficult for us to conceptualize. The light year helps us greatly in understanding these distances. So we have a basic understanding of the light year, but how do astronomers measure these distances to nearby stars and other objects in space? If they really are that far away, what methods can they use? Well, one method that can be used is to measure the parallax of nearby stars to determine their distance. And this works with stars that are up to about a few hundred light years away. So as you saw in the text, you can actually demonstrate this parallax by closing one eye and extending your hand out in front of your face and looking at your thumb. If you switch eyes, close the one that was open and open the other one, you'll see that your thumb appears to move. And if you pull your thumb closer to your face, you'll see, and do the same thing, you'll see that it appears to shift even more. In fact, closer stars also appear to shift more than farther stars, and that's why this method only works up to a few hundred light years away. But in the graphic, you can see that astronomers will observe an object, in this case it's the Pleiades star cluster, in February when the Earth is on one side of its orbit, and then they'll wait till August when the Earth is on its other side of its orbit, which is roughly 300 million kilometers away, and view the same object. By looking at that apparent shift, they have an angle that they can then use to apply some basic trig functions to get a pretty good estimate of how far away that object actually is. And we're going to be using this in a practical application at school to measure the distance of stars from a variety of planets. Okay, let's talk about how astronomers categorize stars. There's a number of ways that stars are categorized, but mainly by color, size, and brightness, as well as chemical composition and mass. And if you look at the chart on the right, you'll see that temperature increases as you move up on that chart. So the top tier, the hottest star we see there, actually would be a blue or blue-white star, whereas the cooler stars at a chilly 3,000 degrees Celsius would be red. Notice that the yellow star, like our sun, is pretty much right in the middle there at about 6,000 degrees Celsius. Categorizing stars by brightness is a little bit more tricky because the apparent brightness, or how bright a star appears to be, is greatly impacted by the distance that star is from Earth, from us here. it might be close and therefore looks to be bright or brighter than other stars around it in the night sky. But that's not 100% accurate, because as you can see on the text here, there is what we call the absolute brightness. And the absolute brightness is how bright the star actually is. Not how bright it appears to us on Earth, but how bright it actually is. And if you know the star's distance from Earth and you know its apparent brightness, you can see it, then you can calculate its absolute brightness. Okay, here's your first look at the Hertzsprung-Russell diagram. The HR diagram is a very convenient way to organize stars, and you can see that on the x-axis, stars are placed based on their color and temperature, and on the y-axis, stars are plotted based on their brightness. So as you move farther on the HR diagram, stars are cooler, and as you move up on the HR diagram, stars are brighter. We'll be using this quite a bit moving forward, but I wanted to show this to you right now so you can see how these stars are organized. Okay, so what exactly is the chemical composition of the sun and other stars like it? Well, most stars are 96 to 99.9% hydrogen and helium. And you might remember talking about that in the previous presentation about how stars actually fuse hydrogen into helium. And in fact, they do make heavier elements as well. And you're probably familiar with the periodic table from last year, the year before, but you can see that hydrogen and helium, in fact, are the lightest of the elements, the lightest two elements, that is. So we'll be talking about where and how all of the heavier elements are, in fact, formed in the future. So a really good question would be, how do astronomers figure out what elements are, in fact, inside stars, right? They're incredibly far away and incredibly hot. So what do? Well, they use an instrument called a spectrograph to study the light that is emitted from that star. And essentially, it takes that light and breaks it into the spectrum. And now the dark lines on there, on that spectrum, are known as absorption lines. And they show where light has been absorbed by elements located within the star's photosphere. And each element absorbs light at a different wavelength and therefore serves as sort of a fingerprint to help us identify what elements are located within that star. Okay, the final main point in this section was on HR diagrams, and I realize I already showed you one, but just again, why are they useful? How are they useful to an astronomer? Well, they're used to estimate the sizes of stars and their distances, as well to infer how stars change over time. In fact, the next section in our text is on the stellar life cycle, like how do stars begin and how do they develop and change over time. You'll notice that most of the stars on this HR diagram, including our sun, is located on this sort of center band, which is known as the main sequence. Outside of that, there are supergiants and giants and white dwarfs. All things, again, we'll be talking about in the near future. Okay, that's it for today. If you have any questions, please feel free to ask in class or just send me an email. Again, next time we'll be looking at sort of the life cycle of stars. This is a nebula, it's known as the Eagle Nebula, and the pillars of creation can be seen in the center of it. It's sort of the beginning, the birth of a star. We'll look at that, how stars change, and the end of stars, what happens at the end of their lives as well. Thank you very much. Take care.